The next item we're going to consider is modeling rotational mechanical systems. And so largely this is going to be the same as our translational mechanical systems. So largely the same as our translational, but we are going to have a few key differences. So let's say except now with our rotational mechanical systems, instead of having our force, F of t, we're now going to be talking about a torque. And so we're going to call that capital T of t. And instead of having a translational displacement, so I'm just going to put translational displacement, which we called x of t, we're now going to be talking about, of course, an angular displacement. And we're going to represent our angular displacement with a theta as a function of t if we're in our time domain. And then finally, instead of having a mass, we're going to be talking about inertia. So in terms of our important constants for each of our three passive elements, for our spring, we still have our spring constant K. So that's still the same. K is our spring constant. We still have a coefficient of viscous friction, but now we're going to refer to that as capital D. So this is our coefficient of viscous friction. Clean that up a little bit. All right, and then finally for our masses, we're going to have an associated J, which is our moment of inertia. Okay, and of course we have a set of equations that relates various properties for these three passive components, particularly our torque, T, our angular velocity, omega, and our angular displacement, theta. So all of these equations, again, mechanical engineers you might be a little more familiar with, electricals you might need a bit of a refresher, but all of that is contained on table 2.5. And in the 8th edition of the textbook, that's on page 61. Again, as of the time of recording, the notes posted on Canvas have the page number for the 7th edition. But again, this table is going to be posted on Canvas, so you can find it there as well. Okay, so just like with our electrical networks and our translational mechanical systems, it's going to be useful to talk about mechanical impedances. And again, the idea is if we do this, we can sort of skip the step of writing our differential equations. If instead we take each of our components and define it by an impedance. So essentially taking our components to the frequency domain. So in general, our mechanical impedances for rotational systems are going to be defined as Z sub m. Again, we have that m subscript to indicate it's a mechanical impedance and not an electrical impedance, as the torque as a function of s divided by the angular displacement as a function of s. So again, notice these are functions of s's. So this torque and angular displacement are the little Laplace transforms of our torque and angular displacement up here, which are in our time domain. Okay, so then our three impedances for sort of our three common passive components that we're going to be dealing with, we have our spring, we have our viscous damper, and our inertia. So for our spring, we have the mechanical impedance for, again, rotational systems is K. For our viscous damper, it's equal to D times S. And for our inertia, we have that our mechanical impedance is equal to J times S squared. And so one other thing to note too is we have the same concept for degrees of freedom as we did with our translational mechanical systems. Same concept of degrees of freedom. And so specifically, our degrees of freedom are going to equal the number of equations that we're going to need. And so more specifically, remember last time we said we had this analogy of if you can hold a point and move, hold all points and still move a point, then that's 1 degree of freedom. So we can have a similar thing here, but it just switches to rotation instead of sort of lateral movement. So number of equations that are required to describe our system is equal to number of points that can be rotated while all other points are held still. And so some of you mechanicals might have a better way to describe that. If so, please feel free to share that with me in the class. Again, obviously I'm an electrical engineer by training, so I don't have as much experience as some of you guys probably have with some of these mechanical ideas. Okay, so that's how we can determine how many equations we're going to need to describe a system. So what we're going to do in the next video is look at a general set of equations really briefly, because it's going to be very similar to our translational mechanical equations. Then we're going to look at an example of how we can use those.